Sir, is there any plan today? Yeah. Just come down to 8 now. Okay, sir. We'll just start this chapter. Sir, this is the first chapter, second subject. Energy efficiency in electrical utilities. Today we'll just start, sir. And most of us are from electrical discipline, I think. Am I right? Sir, is there anyone from mechanical discipline? Sir,
Mechanical, sir.
only Dr. Mary, right? Others are from electrical discipline only. Yes, sir. Am I right?
Yes, sir.
Okay. So the subject on the electrical energy efficiency in electrical utilities comes as subject 3. So we have to pass this subject as a compulsory subject, one of the 3 compulsory subjects in energy manager examination, one of the 4 in energy auditor exam. So there are nearly, I think, 10 chapters are there, I think. The first one is electrical systems. It deals with the basics. Whether we pursue energy manager profession or not, this chapter remains a main chapter or an important chapter for both electrical and mechanical engineers. So we have to be thorough with this chapter, and I will give just hints only, sir. You have to practice. Otherwise, this will be a it is not so complicated, but we have to keep in mind all those things. That's all. The objectives of this particular chapter is we will be learning electrical power supply links from generation to end use, the utility tariff structure and all. We may be dealing with them today or not, because already it is 9:45. Concept of MD, maximum demand, and basics of power factor, basics of transformer, transmission losses, transmission distribution efficiency. That's all. To start with, so the first terminology is heat rate. For a power plant, the heat rate is defined as the heat in joules or kilocalories required to produce 1 kilowatt-hour energy. This is the heat available in the coal. So how many kilograms of coal we are using, the heat contained in the coal. For example, generating 1 unit of electricity, we require more than 700 to 750 kilograms of coal. So in 700 to 750 kilograms of coal, the available heat is will be around 3,500 or 2,500 to 3,000 maybe. That is the heat rate. For every station, heat rate is defined, and the deviation is considered as the difference is considered as the deviation. Actually, no power station in India or anywhere is running with correct heat rate. It is falling behind only. Our aim is to reduce the heat rate. Okay, sir. To start with, the first and foremost, sir, why we are increasing transmission voltage? We are transmitting now up to 400 kV. We are transmitting, sir. What is the reason for transmitting in such a high voltage? Yes, sir. Please tell me, sir. It's very simple question.
Conductor size, sir. Main conductor size. Criteria is conductor size.
Yes, sir. In mathematical formula, sir, what is the reason? It is I square R. Am I right? Yes, sir. Who is speaking?
Yes, sir. Yes, sir.
Consider that too. I square
Yes.
R is okay. For resistance, you have to consider the resistance of the conductor.
Hmm.
There
So
comes the area of cross section. If you go for higher voltage, the area of cross section is very limited, less.
Hmm.
The resistivity of the conductor is less.
Yes, sir.
So the transmission loss will be less.
Uh,
I square R loss will be less.
Yes, sir. Sir, we will come to that later. But before that, I'm asking, what is the I square R loss is the main constraint, right? Yes, sir.
Yes.
Yeah. Yes. Yes. I just want to be clear with the Ohm's law, sir. That's why I'm asking. I'm asking this question for many years with the students. I'm sorry, but I can ask this question here also. Okay, sir. I ask this question. It's a basic question, but I have to ask it. That's why. Otherwise, we will not be clear in the entire subject.
Current is directly proportional to voltage.
Yes, sir. Sir.
It's indirectly proportional to resistance of the conductor.
Sir, sir, we have to contain I square R loss. So we have to reduce the current that is I. We have to reduce I. Am I right, sir? That's why we are raising that's why we are raising V.
Yeah.
Sir, I square R can be written as in another form, V square by R.
Yeah.
Am I right, sir?
Yes, sir.
I is equal to V by R. I square means V square by R square. And I square R becomes V square by R.
Yes.
We are raising the voltage. Will it not rise? This is my question.
Then, sir, if you raise the voltage, then what you are asking?
I square R loss. I square R can be written as V square by R.
Correct, sir. Yes, sir.
He told me that if you are raising V, I will come down.
Yeah.
But I can be written as V by R. I square R loss can be written as V square by R.
Yeah.
If you raise V, once again the V square will go up. Am I right or not? That's what I'm asking.
Once you raise V,
Sir, any answer, sir? Is my question clear? Or am I confusing you? No. Sir, may I know who is speaking? I don't know. I don't get the names are here.
Giridhar, sir. Giridhar.
Yes,
Giridhar.
yes, sir, please.
Actually, I square R is nothing but V square by R. Correct?
Yes.
Both are loss.
Mhm.
If you are asking V, if V is increased,
What is the meaning
Then-
of raising V?
what is the meaning of raising V?
That's what I'm asking. Yes, sir.
Yeah, I'm thinking, sir.
Yes, please. You please think. Until then, I will write one draw one diagram. So I'll try to write a draw one diagram because
Okay.
please think and interrupt me if you find the answer in between.
Okay.
Sir, got any clue?
V is raised, current also raised. Okay. Keeping the load is constant. Yeah, if V is raised, current also raised, then I square R is
Sir, why I'm spending this
size
much?
remains same. If V increases and I increases, if anything increases, but the conductor is remains same, na?
Sir, forget about all those things, sir. I'm just asking. We have to contain I square R loss, so we have to reduce I. For reducing I, we are increasing V. I'm asking if I can be written as V by R, I square R loss can be written as V square by R loss. Then what is the meaning of raising V? This is my question, right, sir? Up to this question is understood.
clear. Question is clear.
Yes, sir. Because actually this problem came to my mind very long back, because the basic Ohm's law is not always clear to all of us, sir. It is always little bit confusing. That's why I'm here taking much time to make it clear. Even if this one session goes for it, it will still work for it, sir. So I am, sir. Sir, supposing we are designing one system, and in this system, this is the power station, this is the load and some. Okay, we are transmitting from here to here. What we are transmitting? We are transmitting power. We are transmitting power. If you are generating 100 watts, 100 kilowatts, we'll be transmitting 100 kilowatts only. That is our aim. Our aim is not to transmit voltage or current or nothing else. We need to transfer the power.
Okay.
Am I right, sir? For example, the car headlight is very powerful, right, sir? It is equivalent to more than nearly, it may be around 200 watts or also the headlight. 200, okay. But what is the voltage there? Just toll load.
Just a toll load.
Toll load.
Yeah.
Voltage, current, those are all immaterial. We need only power. We have to transmit power. That is our aim. Right, sir?
Okay.
Let us assume 100 watts power we are generating, and we have to transmit it to the load end, 100 watts. Okay. In first case, we are keeping the system voltage as 10 volts, sir.
Okay.
This is the line resistance. Okay, 10 volt. What will be the current now?
If it is resistive, it is only.
No, sir. Forget about the line resistance. I am asking if the voltage is 10 volt, what will be the current?
10 amps.
Yes, 10 amps only. Right, sir?
Okay.
In the first case, it is 10 amps. In the second case, sir, we are keeping this voltage as 20. What will be the current?
5 amps.
5 amps. Okay. 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 Say, let us imagine this resistance as 0.1 ohms. Okay, sir.
Okay.
In first case, what will be the loss?
Okay. 10.
I square R means 10 square 100 into 0.1, 10 watts.
Okay.
Right, sir?
10.
10 watts. 10 watts, am I right, sir?
Correct, sir. 10.
In the second case, 5 square 25 into 0.1, 2.5 watts.
2.5.
Am I right, sir?
Yes, yes.
Okay. So our understanding is up to this clear. That means if you are raising the system voltage, we will transmit the power with minimum loss. This is what we are being told, and this is correct also. Only thing, I gave a little confusion, right, sir?
Okay.
This I is equal to what?
Is equal to
What? Is equal to what, sir?
E by R. E by R.
V by R.
Yeah. V by R.
Correct, sir?
Correct.
And this current depends upon the load, sir.
Yes.
Am I right?
Yes, exactly.
It does not depend upon the line resistance.
Correct.
Correct, sir?
Yes, mainly depends on load.
This may be a resistive load or inductive load, whatever it may be, sir. We don't bother about this load.
Okay.
Okay. Then I is equal to V by R. We found one data, I square R, that is equal to what we found just now. First case 10 watts, second case 2.5 watts. Right, sir?
Okay. Yes, sir. Yes, sir.
Yes, sir. Now I square means 10 square into 0.1 and
Okay.
second case. Okay. Now this can be written as I square, or I can be written as what, sir? V by
R.
R. Okay.
Yes.
Yes, sir.
Yes, yes.
Where is that V, sir?
V.
This V is the V across this resistance. This is the voltage drop across the resistance, not this V. Okay, sir?
Okay. Okay. Okay.
Now imagine. Is everything clear now, sir?
Voltage is directly applied to the load only, sir.
Yes, sir.
only applied to the load.
Yes. This I square R is we are calculating here. That means I going through this resistance.
Okay.
R is that particular resistance. We are imagining on concentrated resistor. That's all. Equivalent resistor, not distributed. Then we can write this as we can write this I by I square V square bar. Sorry, I square R loss as V square by R. That V is not this V. It is the V across this particular resistance. What is that V, sir? In first case, we will see. I is equal to 10. And this one is
0.1.
Now, what is the voltage?
1 volt. 1 volt.
Yes, sir.
Yes.
1 square by 0.1.
1 volt. 1 volt. Yes.
1 square by 0.1 is 10.
1 square by 0.1.
1 means voltage, sir. 1 square V square divided by R 0.1. Confusing still?
No, the current is first case. The current is
Sir, don't confuse about first case, second case. We'll take just only one case, sir.
okay. Okay.
Only one case. The current is flowing here.
Okay.
That is, what is that? 10 amperes. Okay, sir. This is the equivalent resistance.
Okay. 10
10
ampere
square.
plus. Okay.
10 square I square R. 10 square means 100 into
Okay.
R is 0.1. Totally we get 10 watts. 10 watts will be lost in this equivalent resistance.
Correct. Correct. Correct.
Like this is the line loss.
Okay. 9 loss.
Yes, sir.
Correct.
This
Correct.
I square R loss can be written as already I told you V square by R. That V is not this terminal voltage V. It is the V that is the voltage drop across that particular resistance.
Okay. Okay.
Okay, sir.
Yeah, okay. Yes. Yes.
You got it, sir. Now,
Got it. Got it. Got it.
yes, sir. To understand Ohm's law only, I am telling all these things. So it will be clear from here, from now on. Am I right, sir? You got a new information or not? Right, sir?
Right, sir.
Yes, sir. Thank you so much. Actually, I wanted to convey this information to all. One more thing, sir.
Tell me.
If we increase the voltage to 11 kV to 33 kV,
Okay.
how much the loss will come down?
One third, sir. 1/3.
1/3 for I, because it is I square, so it will come down to 1/9.
1/9.
Okay, sir.
Oh, yeah. 3 times. 3 square is 9.
Yes, sir. These are all the tiny information I just wanted to convey.
Okay.
And one thing, sir. 1 unit saved is equal to 2 units
Generate.
generated. Is it a thumb rule or actual, sir?
Almost same.
Almost same. Have you referred any calculations so far? Have you come across any calculations?
Yes, sir. Yeah. Previously, some tests
Okay.
approved.
Okay. Yes, sir.
Yeah, sir. Yes, sir. Some cases it was proved.
No, okay, sir. Okay. In this case, I just want to add one more thing, sir. I told in the first class also, the nameplate details of your motor.
Yeah.
For 10 kilowatt, what does it indicate? It indicates.
Mechanical output.
Yes, sir. Exactly, sir. Yeah, that's the shaft power output.
Shaft output.
Yes. That is the useful energy we are getting from the power supply. Is there any doubt, sir? So
No.
this is the end. This is the end. That is shaft power output is the end. Generating end is the generated power station. Okay. So we have to calculate from this end to that end. Okay. Now we'll be looking for a sir. Can we use any calculator or mobile phone for calculation, sir?
Okay, can you see?
Please open up one calculator, sir, in your mobile, sir, so that it will not be forgotten. Simple only, sir. Just calculator mode, just multiplication. No scientific calculator is needed.
Okay, tell me, sir.
So you have opened. So
Yeah.
You'll be giving me the answer.
Tell me, sir.
Sir, the first and foremost loss in a thermal power station.
Yeah.
After generating. Sir, just a minute.
After generating line loss.
No. Beyond generator terminal, sir, what is the first loss?
Beyond
Terminals of a generator in a power station, what is the first loss? Forget about those auxiliary consumption and all.
That is transmission loss, sir.
No, the very first, what I'm asking with the very first loss.
Very first loss. After generation.
Terminals of a generator. There is one step up transformer.
Okay.
That will be raising the voltage to 400 kV.
Okay.
That is that is generation transformer.
Okay.
Generation transformer. Generator transformer is the first load. Will be losing energy. What is that percentage? That is, it is the most efficient of all equipment in the power station.
Correct.
99.5%.
99.5. Correct. For transformers.
So, yes, sir. You just type 0.995 in the first class. 0.995.
Okay.
Okay, sir. What is that second, sir? The 400 kV transmission, it is highest voltage, so it will be having lowest transmission loss. That is nearly 1%. That is 99%. You have to multiply it with the previous one with 0.99. Already we had 0.995. Now put
0.995 into
0.995 into 0.99. This is 400 kV transmission.
Okay.
Again, it goes to 230 kV, stepping down, and again transmission. The step down transformer with that transmission, 230 kV transmission together, we take it as 97.5% efficiency. So multiply it with 0.975.
To 0.975. Okay,
sir. Again, for 110 kV. For 110 kV transmission, it is 0.96% efficiency.
0.96.
So, yes, sir. Multiply it with 0.96. Again, for 33 kV, it is 0.995. These are all typical values, sir.
Okay.
All these things need not be the exactly same. These are typical values.
Okay.
And then for lastly, you have put 0.995, right?
Correct, sir.
Yes. And then for 11 kV, you put 0.95.
Okay.
Again, it goes to a consumer. For an HT consumer, the transformer efficiency will be around 0.95 only, sir. So we have to multiply it with 0.95.
Another 0.95.
Yes, sir. Yes, sir. Consumer end, HT consumer. And then there will be a great LT switchgear network. This switchgear will lose 5%. So again, you have to multiply it with 0.95.
One more 0.95.
Yes, sir. And comes the
Okay.
motor. The motor efficiency is 0.9.
Into 0.9.
Yes, sir. Again,
Okay.
last comes the mechanical power. The mechanical power coupling and everything. The mechanical power, it is the lowest efficiency. Will be losing much energy in the mechanical coupling. It is 70% only. So we have to multiply it with 0.7.
Into 0.7 only.
Yes, sir.
Okay.
How much you got, sir?
Only 0.5 is coming.
Yes, sir. So we generated one there.
Oh, correct. You have come to the point.
Yes, sir. Yes, this is a simple exercise. I am treating you all as a students, but it is needed, I think. Useful or not, sir?
Very much useful, sir.
Sir, useful, sir. Useful, sir.
Thank you, sir. Thank you so much, please. Yes, sir. Now, I am not prepared the PowerPoint, sir. So I'm rushing up with the data. Sir, the losses are termed as T&D losses, sir. Transmission and distribution losses. All these things are called technical losses, and commercial losses means pilferage will be there, and the payment and all together combined as technical and commercial losses. But we will be dealing with the T&D, transmission and distribution losses only. We term it as in Tamil Nadu, we are considering it as 17%, sir. In Jammu and Kashmir, it goes up to 50%.
D&D loss is 17% totally.
In Tamil Nadu, it is 17%, sir.
1/7. Okay.
Okay, sir.
But the benchmark is 13%, isn't it? Benchmark.
Benchmark, I am not sure, sir. I am not sure.
Okay.
Yes, sir. 13%.
Bala? Is it Bala?
Yes, sir. Yes, sir. Yes, sir.
No, only I am hearing. Yes. Okay, sir. And one more thing, the maximum demand. Maximum demand is levied for the consumers, CST consumers, you know very well. Because why the maximum demand is considered so important, sir? Because let us think otherwise. For the peak hour of 2 hours, the maximum demand will be 17,000 megawatt, more than 17,000 megawatt for Tamil Nadu. Am I right, sir? If we can distribute that 1,000 megawatt to some other time of a day, what will be gain? We can postpone the investment for 1,000 megawatt, that may be around 8,000 crores, to some 10 years from now. Correct, sir? That peak hour demand, if we can distribute it to some other hours, non-peak hours, we need not build a 1,000 megawatt power plant for another 10 years. That's why the maximum demand levy is imposed. It's a part of demand side management. Okay, sir.
Okay.
Yes, sir. We may get a problem in this for 2 marks or 3 marks, sir.
Small
Or
doubt,
what?
sir. Small doubt, sir.
Yes, sir.
You are telling 17,000 megawatt. I mean,
Yes.
that is a peak hour
Uh-huh.
maximum demand for Tamil
Mm.
Nadu.
Mm.
If you distribute it and you are telling like that, how much you can distribute? You can only chop off something, 2,000 megawatt. That's all. Not maximum. All the loads cannot be chopped off.
Yes, sir. I'm telling just 1,000 megawatt only. I'm telling.
Oh, 1,000. So
1,000.
you are
No.
limiting to 16,000 and 10,000
Ah.
can. Yeah.
For 1,000 megawatt itself, we need more than 8,000 crores now.
Oh, yeah.
Actually, I'm told Bala has to clarify it. In Kerala, they have supplied at a very cheap cost 10 years back the CFL light, and the demand has come down to 500 megawatt, I think. Am I
Oh.
right, Bala?
Yes, sir. It's actually, as your word said, it is peak valley and peak shaving. So
Yes.
it's something like whatever automation we have designed is something like whenever there is a peak load, that peak load can be categorized as a load which can be utilized for some other time period. So maximum whenever we go to the toilet for in the morning hours for brushing, you would see that the water is not available and you would switch on the tank. So that is to pump the water to the over tank. That is the first objective we would start. Every houses would be doing the same thing, and that's how it has been categorized as a peak load. If that is going to be shifted to the night time, so in the morning hours, the full tank would be there and no one would be switching on. This is called peak shaving. So peak valleying is something like whenever there is a time period, 11 o'clock time period, no one would be utilizing any power after going to the office. So it's going to be any AC load, it is going to be the common load, or heating load, it is going to be the office load and the other part of the world. If that is going to happen, when we switch on this mixie, grinder, or other things through automation, like washing machine, now it is automated one. After 11 o'clock, the valley, which is having no load, it can be bridged in such a way that it would be a straight line, which would be crossing in the, it would be a linear load. That is what been called as maximum demand, which is shifted to peak load or peak valleying. So that's how it has been designed. So the maximum demand, as you said in the common word, the maximum demand which can be utilized can be peak shaved or peak valleyed. This is how the design has been worked on for DSM, where the incentive plan is also been applied, but no such things are working with the TNEB. But PATCEL can contribute for such things. So
Yes,
PATCEL was designed in such a way that the peak shaving and peak valleying can be incentivized so that the people can understand the value of why the peak load need to be shaved, so that this much crores of amount which is spent on generation can be minimized so that it can be conserved. So as you said, as you pointed out, 0.5%. So that is going to be 1 unit generated is equal to 2 unit, 1 unit conserved is equal to 2 units generated. It is the value, it's not a mathematical formula, but it is the actual that can be applied to the loads that we are consuming.
Yes.
So you clearly explained it, sir.
Yes.
Thank you, sir.
Yes, sir. Actually, I think I got 1 5-mark question during my 2011 exam, energy management exam. I think your what you said, the peak clipping and peak valley and all those things. I drew the examples, and I must have got full marks for that, I think. Because
Very great, sir.
One more thing, sir. In the same line, I'll be telling one more example. Why we are stressing to use solar water heater? Because 1 unit of 1 kilowatt hour energy is equivalent to 861 kilocalories. Sir, please keep this in mind. 1 kilowatt hour heat energy contained in 1 kilowatt hour is equal to 861. That is, we are taking it as 860. you can convert it joules per second, you can convert and you can easily find it. It is equal to 860. For example, we are heating water for bathing and other purposes, 1 unit of electricity, let us assume. So if you use 1 unit of electricity to take bath for entire family, the heat transferred from electricity from the mains to the water will be 860 kilocalories only. Okay, sir. Is that
Yeah.
clear now? Yes. If you assume it as 100% efficient. Okay. For this 860 kilocalories, how much we are spending at the power plant? Let's go back, sir. If we go back, for this 860 kilocalories, for this 1 kilowatt of energy, we will be using 2 kilowatt, 2 units of, we have to generate 2 units of electricity, right, sir? At the power plant.
Yes.
In that power plant, for generating 1 unit of electricity, we are using nearly
For utilizing
Sir.
1 kilowatt hour.
so utilization is different. So now I'm telling about the generation. Here we are utilizing 1 unit.
Yeah.
There we are generating 2 units.
Correct.
Yes, sir. How much coal we are using? I am just comparing. For generating 1 unit of electricity, we need to burn nearly 700 to 750 kilograms of coal. Yes, sir.
Okay.
In 700 kilograms of coal, the kilocalories contained in that particular coal is equivalent to how much? 700 into 3,500. How much we will get? We will get more than 2,500 or 2,700 kilocalories for generating 1 unit.
700 into 3,500.
Yes, sir. 3,500 is kilocalories per kg of coal. We are using 750 kg only, 750 grams only. That's why we are multiplying it with 0.75. Nothing else. 1 kg of coal contains 3,500 kilocalories, sir.
Okay.
We need only 700 kilograms, 700 grams of coal to generate 1 unit. So,
Okay.
so we have to multiply it with 0.7 or something. Okay, sir.
Okay.
Is it okay?
Into
So,
0.7.
yes. So for generating 1 kilocalorie, 1 unit, we'll be using around 2,000.
450.
Okay, sir. 2,450. You got the calculator with you, right? Okay. 2,450. But we have to generate 2 units, right, sir?
Correct.
So it will be 5,000.
Exactly.
5,000. For getting 860 kilocalories of heat, we have to burn
5,000 kgs.
5,000 kg.
Yes.
Okay, sir.
Cool.
Almost 1/5.
Exactly.
That is why solar water heater is very much advised. We are generating solar electricity, PV electricity, but we are not utilizing the solar heat energy. This 5,000 kilocalories will generate how much of
5,000 kg.
Yes, sir. Yes, sir. This will generate nearly 2 kilograms of CO2.
Oh, yeah.
Yes, sir.
Emits.
Yes. For generating 1 unit of electricity, the thumb rule is we'll be generating 1 kilogram of CO2. For 2 units, we'll be generating 2 kilogram of CO2. So saving electricity means saving the earth from generating CO2.
You can say 1 kilowatt hour is directly proportional to 1 kg of CO2, sir. Directly.
Yes, sir. We can say so easily. We can say. I calculated many times.
Okay.
This is not applicable to ETPS like power plants. Or ETPS is very old. It is now closed. It will generate much more, sir. For generally 210 megawatt and above, they generate. The international rule is 1. Some else will be generating at 1.2 kilograms per unit.
1.2 also.
Also, thumb rule is 1. We can take it as 1.
Okay, sir.
Yes, sir. Okay, sir. I think we have reached 10:30.
So that means to say 5 tons is equal to 1 kilogram of carbon dioxide emission. So that much heat has been extracted and 861 kilocalories has been utilized and the rest of the heat has been wasted. When we can improve the efficiency by 33% to 50%, it may yield some more. So
yes,
that's
yes,
how
definitely. Combined cycle. Yes, you're right. Cogeneration and all.
Yes, sir. So maybe as you started, you were talking about electrical engineering. So the more we talk about electrical engineering as the universal source, the mechanical and civil people need to work on for containing these radiations or the heat as a convection, conductions, and radiations. This need to be curtailed to improve the efficiency in such a way that the mechanical efficiency is improved on chemical part. If chemical efficiency is going to be improved, then this anthracite or bituminous coal can have a calorific value 4,800 also. So in such cases, 4,800 kilocalories can be burnt at the rate of this much carbon emission is being reduced means. So we need to improve the heating which reduced as ashes. So it's all depend on the raw material with the heat cycle and then coming to the conservation principle. So the last line is conservation. That means to say we have not concentrated more on this energy pyramid. So we need to work on with the energy pyramid. We have more such things on energy audit itself, sir. Kumaresan is also preparing on it. We will have Kumaresan sir working on with the energy audit as well as the second book he's working on. So by yes, sir. By tomorrow, who is going to take up this classes, sir? Kumaresan sir, are we?
So day after tomorrow, but because tomorrow is my shift, so I'm not able to take the class tomorrow.
Okay, fine. So then let's have Mary ma'am. So like I'm today we had a very great interactive session. It is a good objective that we can understand what is actually taught for many hours of books that is been symbolically represented by Prathaman sir. It is great to understand that 2 units is being conserved or generated. So whatever point that has been in the theory, it was directly proportional. 1 unit generated is equal to 2 units conserved, and the vice versa is also possible that we need to work on with engineering activities. As we all engineers working on such parameter, we don't understand the reality, and we are contributing for carbon emission, and we could not work on with carbon mitigation, that is to climatic mitigations. In such aspect, we need to work on with efficiency. So we need to go through such things. It is not for completing this energy manager or energy auditor examination, but we need to understand the reality that why these boilers are emitting this much pollution, or why the efficiency is not been manipulated to in order to bring about a change. All these PhDs are been tabulated as a PhD, but none of these are going to be the working principle for enhancement. So let's make a point that at least we can join together to make an environment safe. So that's how we need to work on. So this objective would pave the way for succeeding this climatic action. So we'll reduce this carbon pollution for the future.
Yes.
Thank you so much, sir. We'll work on.
Yes. I just want to remind one more thing. In all these calculations, we left out one thing, sir. We have not included. If you include that, the loss will be much more. The auxiliary energy consumption. It is around 8%, sir. Auxiliary energy consumption we have not included. If you include that, It will be
8%, 8%, sir?
yes, sir. Yes, sir.
It's 12.5% for lower value. It is going to be rising trend for higher ratings, sir. So
for full load.
that's how it has been raised to 800 megawatt right away.
Okay, okay, okay.
This 8% is only for full load generation, sir. If you
Full
are
load generation. Yes, sir.
for partial load, it will be much more, sir.
Sir, one more basic doubt, sir.
Yes, sir.
Regarding coal and lignite,
Hmm.
calorific value difference is the criteria or any other criteria is there?
Sir,
Is
the ash content, carbon content is very much less in lignite, sir.
Okay. Actually, what we are using in thermal stations and all, lignite or
No, sir, no, we are not using lignite. So lignite is used only in the NLC, sir. We are not
NLC.
using. Yes, we are using that subbituminous only.
okay, okay.
Yes, sir. To add your point, so anthracite is the oldest coal that is having a higher value up to 4,000 to 5,400 kilocalories, which is not available in the entire world. Australia is the one resource which is having such kind of anthracite, but our ministers has looted it. So, okay, we need not talk about such things. That is one thing we need not work on. Bituminous is other part where it is available in Indonesia and Australia and South Africa. So that is being burnt in all the boilers right now. It is bituminous coal, which ranges from 3,500 to 4,000 kilocalories. That is the maximum that can be achieved through it. And the third quality is lignite, where the moisture content is very high. And the sulfur dioxide content is also high, which leads to pollution. So that's how lignite should not be burned. When comparatively, Tamil Nadu Electricity Board has lesser generation than NLC, where NLC itself has got 10,000 megawatt of energy through thermal power plants. And that's how they have installed solar power plants throughout the area, and they has also made it that pollution need to be curtailed through some contributing to the renewable energy. So that's how NLC has contributed a lot to the society. But coming to one another point, as you asked whether this lignite can be used, means that is the only available resource which is least. That is, it would take billions of years to convert this plant waste to coal. So in such aspect, lignite is the which is very youngest. So oldest is going to be anthracite, means eldest, that is younger, is going to be the lignite. So younger is going to be lignite is always available around us. So NLC is expanded up to Ariyalur near Trichy. So if the mining is going to happen beyond the limit also, it may lead to a lot of disaster where the water which is being sucked out. If 2 hours of mining is not happening without pumping the water, the entire NLC will be submerged. In that aspect, the water table is also reducing. So all these things need to be the climatic action which leads to landslides and other thing which is not been noted down. So why we talk about energy means the energy is universal source. Without energy, we can't even listen to this Zoom meeting. So that is the main part that we need to talk about. But the pollutant for mere energy, the climatic action, which is eating up all the resources as well, and also killing more people who are living in natural vegetation even without power. Tangetco has the pride that it has installed, electrified the entire revenue yielding village by 1985 itself in the entire country. This first of its kind. But still, even today, Tangetco has not provided lighting to all the people in entire Tamil Nadu. In such aspect, if 3 crore 22 lakh consumers are going to be benefited out of it, but we need to worry about this much crores of people doesn't have power. The only aspect to conserve energy is that we need to understand that at least everyone is going to taste this energy. Whatever technology we have given, we need to give it to equality as well as equity. So we need to know the difference. Okay, but anyhow, we need to talk more about it. we don't have time. So as Parandaman sir used to say these words, so we don't have time to go about completing the syllabus. We would have the aspect in bringing climatic mitigations and other things to be understood in common words. Again, I thank Parandaman sir for making it so simple and making it understandable that V is equal to IR is Ohm's law, which is not applicable every time, and all the loads which has been manipulated cannot be equated with a formula. It's a good concept, sir. So we need to appreciate Parandaman sir as well as the teammates who are contributing, and particularly Giridhan sir. So thank you so much, sir.
Thank you, sir. Thank you, sir. Thank you.
Thank you.
Sir, about tomorrow's program, sir.
Yes.
Can we complete this particular chapter? I just started only. Can we complete it tomorrow?
Yes, sir. With pleasure, sir.
Yeah. Okay,
With
okay.
pleasure, sir.
Okay, sir. About chapter 10 and chapter 11, some part is missing. We have to complete, but we will take it to the end, I think. Otherwise, we will not be completing the problem. If we get time, we'll do it in the end of the month. So tomorrow we'll be completing chapter 1. If we are unable to complete that particular chapter tomorrow, we will leave it. We will not use the day after tomorrow. So we have to confine ourselves to 1 chapter per day. Then only we can complete within the scheduled time, sir.
Yes, sir. We will plan it accordingly, sir.
Okay, okay, right, sir. Thank you. We'll leave now.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you.
Thank you very much, Parandaman.
Thank you, sir. Thank you, sir.